Okay, good morning, everyone. So before the midterm, we had been talking about 3D problems with spherical symmetry. And so for such problems, there's a complete set of commuting observables for 3D problems. And we're interested for now in these problems with spherical symmetry. And so our complete set of commuting observables is going to consist of the Hamiltonian and the total angular momentum squared. And then we get to choose one of the three components of angular momentum because the others won't all commute with each other. So we choose that to be L sub z. Okay, and we already know what the eigenvalues of these are. For L sub z, the eigenvalues are h bar m. For L squared, the eigenvalues are h bar squared, L times L plus 1. And now, depending on what the potential is, we need to find out what the eigenvalues of the Hamiltonian are. But because we have spherical symmetry, we know these all commute, and so they have simultaneous eigenstates. So there are common eigenstates, which we label as psi sub ELM. Those are kets in the Hilbert space. And now, if we have those kets, we can construct the corresponding wave functions. Okay, so again, they're labeled by the three eigenvalues of the complete set of commuting observables. They are functions of r, theta, and phi. They're given by the inner product of the eigenstates of those position coordinates acting on the ket. Okay, and we showed before that we could separate this into a radial part that depends on E and L and the radial coordinate, and an angular part which depends on M, L, and M and the angular coordinates. Okay, so one thing to keep in mind is the radial part doesn't depend on M, and the angular part doesn't depend on the energy. Okay, so now if one plugs that into Schrodinger's equation, which is what I think is the last thing we did last time, we get the following. So minus h bar squared over twice the mass, which, reminder, mu is what we're calling the mass, so we don't get it confused with the magnetic quantum number. 1 over r squared partial r squared partial r, minus L times L plus 1 over r squared, all acting on our radial wave function, is equal to the energy minus the potential acting on our radial wave function. So what happened was the spherical harmonics were just multiplying the whole equation, and so they canceled out. And so what remains to be done is to simultaneously solve for the energy and the radial coordinates, the radial wave function. So E and R sub EL are to be solved for. So when we do this, we fix L and we fix M. Actually, M doesn't affect anything in this equation, but we fix L, and that changes what this is. This whole part on the left is all coming from the Laplacian and the Schrodinger's equation. And so we have to solve this thing. Okay, so it turns out to solve this equation, it's useful to do a sequence of changes of variables. So the first thing we're going to do is just to make things more elegant. So we're going to define a new function, which we're going to call u. And u is just equal to little r times big R. Notice I'm not going to always put the subscripts e and l on here because they would just take up clutter. And we know these things depend on e and l. Okay, so we've defined this new function. And why is that a useful thing to do? To answer that question, let's compute its second derivative with respect to r. Okay, so by the product rule, that's d by dr acting on capital R plus little r times the first derivative of big R. And then we do it again, and we get 2 times the first derivative of big R plus little r times the second derivative of big R, which we can rewrite as something that looks suspiciously like the thing appearing in Schrodinger's equation, namely 1 over r d by dr of r squared, derivative with respect to r. So we recognize that that is almost the same as this. It just needs an extra 1 over r factor. And so we can plug that in, plug in everywhere for u, big R for u. Okay, and so we get minus h bar squared over 2 mu, 1 over r, second derivative of u, times u over r equals E minus the potential times u over r. Okay, or by just multiplying through by r and moving the v over to the other side of the equation, we get minus h bar squared over 2 mu, second derivative of u, plus, and I'm going to group together two terms. There's a term from the potential, and then there's a term from the L's. So this is h bar squared over 2 mu L times L plus 1 over r squared. All multiplying u is equal to the energy eigenvalue that we're trying to find times u. Okay, so that's our Schrodinger's equation for u. And so we note that this is similar to just the one-dimensional Schrodinger's equation. So we've sort of turned this three-dimensional problem into a one-dimensional problem with the following changes. Instead of the usual one-dimensional coordinate x, we're now dealing with r. Instead of the one-dimensional wave function, the thing that we're solving for is u. I'll put back the subscripts. Okay, and then once we solve for u, we have to remember that we need to go back up here. To get the radial coordinate, we have to take that and divide by r. Okay, but then there are two other changes that we have to keep in mind. One is that unlike in a one-dimensional problem where typically x goes from minus infinity to infinity, so I should say here except, okay, we have instead that 0 is less than or equal to r is less than infinity. And that's simply because the radial coordinate can't be negative. So if we're solving a one-dimensional problem, we might have just decreed that we were only interested in positive x, but here we can't possibly talk about negative r because there's no such thing as negative r. So that's one change, and the second change is that the potential is modified. So the potential in this one-dimensional effective problem is V of r plus an extra part that's dependent on the angular momentum. So if the angular momentum is 0, this extra part won't be there. But otherwise, it goes like 1 over r squared. Okay, and this combination is called the effective potential. And if you've taken a classical mechanics class on central force motion, you'll recognize that really it's the same thing. It's just that instead of L squared, the classical number, now we've replaced it by h bar squared L times L plus 1, which is a quantum mechanical eigenvalue. Okay, and so that part is called the centrifugal potential. It's what you add to the normal potential to get the total effective potential. And notice that it's repulsive, always, because L is a non-negative integer. So at best, it does nothing, which is the case when L equals 0. But otherwise, as a function of r, the centrifugal part of the potential just falls off like 1 over r squared. And so it's going to push you, all other things being equal, it's going to push you away from r equals 0. Okay, so now we've boiled it down to solving a one-dimensional problem, which is one of the reasons why solving one-dimensional quantum mechanics problems is not a waste of time, even though we live in a three-dimensional world. Okay, so for a while, we're going to be exploiting this to treat various different problems, and we're going to start with the easiest thing we can do, which is a free particle. So that means the potential, and now I'm writing it as a function of the operator r. That's 0. And we're doing this in spherical coordinates. Okay, so before doing that, remember that we already have a solution to this problem using a different complete set of commuting observables. Recall that the wave function is for a certain set of commuting observables is e to the I p dot r over h bar, and then normalizing it gave us a 2 pi h bar to the 3/2. 3 because there are 3 dimensions. Okay, and these are eigenstates of px and py and pz, which are our complete set of commuting observables. And they're also eigenstates of the total energy, because the total energy eigenvalue is the sum of the momenta in the 3 dimensions squared divided by twice the mass. Okay, so these are plane wave solutions. So we already know that, but now what we want to do is have an alternative complete set of commuting observables. We want the basis for the complete set of commuting observables that gives the eigenvalues E and L squared. I guess to be consistent, I should call them all operators. So let's call them H and L squared and L sub z. Okay, so certainly a free particle is spherically symmetric. There's no potential at all. So that certainly commutes with any rotation that you want to do. So now what we can do is go back up to our boxed equation here. And we're just going to plug in this thing with v is equal to 0. We're going to set that to 0. Okay, and so our boxed equation with v of r equals 0, once you multiply through by 2 mu e over h bar squared becomes second derivative with respect to r plus 2 mu E over h bar squared minus L times L plus 1 over r squared. All of that acting on our u. And remember, when we solve for u, again, we have to divide by r to get the real radial wave function. That's supposed to equal 0. Okay, that's special for the free particle. And now we're going to give this combination right here a special name. We're going to call that k squared. Okay, so k squared is twice the mass times the energy divided by h bar squared. And the units of k are 1 over distance, so 1 over meters. Okay, and so now we're going to do another change of variables, this time on the independent variable, the radius, and we're going to define a rescaled radial coordinate by saying that r is equal to rho divided by k. So if k has units of 1 over distance, then rho is a dimensionless rescaled radial coordinate. So this illustrates a general fact that things often become more elegant if you express them in terms of dimensionless quantities. By expressing everything in terms of dimensionless quantities, things will tend to become nicer. Let's see how that works. So first of all, when we do this, we're going to have to deal with derivatives with respect to r, and that should have been a second derivative. Okay, and so let's figure out how that works. So a first derivative with respect to r is k times d by d rho. And a second derivative with respect to r is therefore k squared times the second derivative with respect to rho. Okay, and so if we plug those things in, so now we're expressing everything in terms of u and rho, we get second derivative with respect to rho plus 1 minus L times L plus 1 over rho squared times u of rho is equal to 0. So a nice thing that's happened when we write this thing in terms of a dimensionless number or dimensionless coordinate is that notice that now there's no E anywhere in the equation. So not only did we get rid of E in the angular part, we even got rid of E apparently in the radial part, which almost sounds too good to be true. And in fact, it's sort of not quite true. So the equation indeed does not depend on E, but it's hidden there inside the definition of rho. So what that means is once we solve the equation, it's nice that our solution won't depend on the energy. But once we solve it, then when we go back to the original variables, it will reappear because R depends on rho and K depends on the energy. And so that will reintroduce the energy dependence, which hopefully will reassure you that there's no hidden magic going on here. So meanwhile, though, while we're solving this thing, it's good that this thing doesn't depend on the energy. And so let's systematically solve this, and we'll solve it by first treating the simplest case, and that's when L equals 0. So first, suppose that L equals 0. We'll come back to other values of L shortly. Okay, and so now this part isn't even there. And the equation's really simple, and you can even write down the solutions basically by inspection. There are 2 of them. Okay, so one of them is, I'm going to call it u sub 0 of rho. One of them is going to be cosine of rho, and the other one's going to be sine of rho. Both of those solve the equation. Notice that when we go back to the radial coordinate, cosine of rho is going to become cosine of kr. And that means our radial wave function is going to be cosine of kr divided by r, which is going to go like 1 over r. And so this solution is actually no good at r equals 0. Now notice I'm not saying it's no good at all, because we might be dealing with a problem, and in fact, it's very common to deal with a problem where we don't care what's going on at r equals 0 for some reason. Maybe there's a infinite potential that's everywhere enclosing some region involving the origin, and then we don't care what happens at r equals 0, and this is a perfectly good solution. But if we do include the origin, r equals 0, as part of our allowed region, then this solution's no good. Okay, on the other hand, sine of rho is sine of kr. And so the radial coordinate in that case is sine of kr over r, which is proportional to k, a constant, as r goes to 0. Okay, and so this is okay at r equals 0. So to summarize that, we have two solutions. We're going to keep both of them for now. So I should say for L equals 0. And we're going to label them as A and B. The A one is going to be the good one, which is sine of rho. There's an overall multiplicative factor that we're not going to worry about because that's going to be normalization that we'll fix later. Okay, so this is good at r equals 0. And then u0 of b for bad is cosine of rho. This is bad at r equals 0. Okay, but including both of these, we use these as seeds to find solutions for other values of L. And the process of doing that is one of those things that's sort of not so obvious until you already know how to do it, and then it looks nice. It's a change of variables yet again. So yet another change of variables. And so what we're going to do is we're going to write UL of rho is equal to rho to the L plus 1 power times another function that I'm going to call f. So FL of rho. Notice that means this is equal to rho times the original wave function if I write it as a function of rho. Okay, so now use that change of variables and plug it back into this equation right here. And see what happens. And what you get is that 2 rho derivatives plus 1 minus L times L plus 1 over rho squared, now acting on rho to the L plus 1 times F sub L, that's 0. And so when you take all the derivatives, that implies that the second derivative of F sub L plus 2 times L plus 1 over rho times the first derivative plus f sub L equals 0. So it's not obvious that we've actually made any progress. In fact, cynically, you might look at that and say we've made negative progress, because before we had something that only had 0 derivatives or 2 derivatives, and now our equation has 2 derivatives and 1 derivative and no derivatives, and so it looks like it's gotten more complicated. Okay, but here's the claim, is that let's say you have a solution of this for some L, then you can construct a solution for any other L. So let's see how that works. So first of all, we know that F0 of rho is equal to R0 of rho. So that's nice. That means if we have F0, which we do, then we get the radial coordinate, it's just equal. So notice that comes from here, plugging in L equals 0. And so here's the claim that makes this change of variables worthwhile. If F satisfies the boxed differential equation, the previous box, for L, then I can define a new function g, which is minus 1 over rho times the derivative of f. And that will do it for L plus 1. So in a way, it's kind of similar to the harmonic oscillator. We start with the lowest thing, and then we build up the higher things from it. Okay, and so what does that mean? More specifically, the differential equation satisfied by g is second derivative plus 2, and instead of L plus 1, I'm going to write L plus 2, because that turns out to be right. Okay, and so that's the same equation with L plus 1 replaced by L plus 2, or L replaced by L plus 1 equivalently. So I'm not going to give the detailed proof of this. It's just sort of tedious, and there's nothing particularly enlightening about it. The strategy is to just plug in for G, and then eliminate derivatives, specifically the second derivative of f, whenever possible, using the boxed equation. Okay, and then that gives this equation right here, which proves what we're trying to prove. Okay, so what does that mean? That means for each of our solutions at L equals 0, and remember we're calling them A and B, okay, we have, first of all, we have an equation for L equals 1 solution. F1 is minus 1 over rho derivative with respect to rho acting on F0. So I could put a subscript, or sorry, a superscript A or B on this, because it works for both of them. And now I just keep doing this, and every time I act again with this factor here of minus 1 over rho d by d rho, oops. Okay, we get a solution with one higher L. So that means F2 is minus 1 over rho d by d rho of F1, which is otherwise known as minus 1 over rho d by d rho, acting twice on our F0, okay, etc. And so if you think about it, that means F sub L is simply given by acting L times with that differential operator, taking a bunch of derivatives on F0. Okay, so let's see how this works for in particular. So F0, the A solution is equal to U0 A solution of rho over rho, which is sine rho over rho. And F0B of rho is U0B of rho over rho, which is minus cosine rho over rho. The minus sign is just a convention. Somebody long ago decided it would be more convenient if that had a minus sign. There are actually good reasons for that that we'll maybe see later. Okay, but given those as seeds, therefore at L angular momentum, there's an A solution, which is gotten by acting L times on sine rho over rho. And there's a B solution at total angular momentum L, which is minus 1 over rho d by d rho, L times acting on negative cosine rho over rho. Okay, and now we can plug back in. Let's go back up here to, where was it? This equation right here tells us if we have the F's, then we can get directly to the radial wave function as a function of rho. And so just for the record, let's do that. So then the radial wave function for angular momentum L A solution is equal to rho to the L minus 1 over rho d by d rho to the L sine rho over rho. Notice you have to resist the temptation to somehow combine this rho to the L with this differential operator to the Lth power. You can't sort of move the rho to the L inside because the operation of taking a derivative does not commute with multiplication by the same coordinate. Okay, but anyway, that's the solution. For any L, you can go ahead and do the derivatives you need to do. And these are called spherical Bessel functions, and they're by convention written as J sub L as a function of rho. These are spherical Bessel functions. Spherical Bessel functions are actually easier than ordinary Bessel functions. They're just written in terms of trigonometric functions, like here. Notice that when I take rho derivatives, sometimes they're going to be turning sines into cosines or vice versa. So it's going to be a bunch of sines and cosines times a rational function of rho. So those are the A solutions, the ones that are good at r equals 0. And then the B solutions look similar, except that now it's minus cosine rho over rho. And by definition, these are called spherical Neumann functions. And people have devoted a lot of time to understanding the properties of these. I'll just tell you some of their properties without going into the mathematical details. So first of all, let's write down the lowest few, just to get an idea of what they look like. Okay, so J0 of rho, we basically already know is sine rho over rho. n0 of rho is minus cosine rho over rho. And again, the minus sign was somebody's idea that that's how the spherical Neumann function should be defined. Then you can go to J1. You do the derivatives and you find out this is sine rho over rho squared minus cosine rho over rho. And for N1, it's minus cosine rho over rho squared minus sine rho over rho. Okay, and then you can go to J2, for example. I'll just do the spherical Bessel function for L equals 2. Turns out to be 3 over rho cubed minus 1 over rho times sine rho minus 3 times cosine of rho over rho squared. Okay, and you can keep doing this as much as you want. There's some useful things to notice about how these things depend on rho for small rho. Remember, rho is a rescaled version of the radial coordinate. So for small rho, JL of rho turns out to be proportional to rho to the nth power divided by 2L plus 1 double factorial. So if you haven't seen double factorials before, it's not the factorial of the factorial. 2L plus 1 double factorial means you start at 2L plus 1 and you keep multiplying by smaller numbers that differ by 2 until you get down to 1. Another expression for this is it's the quantity 2L factorial over 2 to the L times L factorial. So that's just a definition, but it turns out you also need this for minus 1, and minus 1 double factorial is just defined to be equal to 1. Okay, so what does that say? That says the A solutions are nicely behaved at small rho. In fact, they go like the radius to the power of the angular momentum. The bigger the power of the angular momentum, the smaller they are near the origin. Okay, but for the Neumann functions, it turns out to be sort of the opposite. As we've already mentioned, these are not well behaved at the origin. So they turn out to go like negative 2L minus 1 double factorial over rho to the L plus 1. So as promised, these blow up as rho goes to 0. Okay, so those are bad solutions if you insist on including the origin, but they're still okay for a otherwise free particle that's excluded from the region r equals 0. All right, so some useful properties of this. Well, first of all, that's for small rho. Maybe we should say what they look like for large rho. And it turns out for large rho, the spherical Bessel functions behave like 1 over rho times a trigonometric function, which turns out to arrange itself into sine of rho minus L pi over 2. So the L pi over 2 is an angular momentum dependent phase factor that just says how rapidly or how does this thing oscillate at large distance. So this is oscillating at large distance, but then it's also being suppressed like 1 over the distance when you go far from the origin. So it's also okay for large distance. And then the spherical Neumann function looks kind of similar. So it also goes like 1 over rho, but there's a minus sign. And then instead of a sine, it's a cosine. So these represent outgoing spherical waves. Okay, the 1 over r or the 1 over rho is just a thing that's there to basically conserve probability. If you have a spherical wave and you're getting far from the origin, the wave has to get smaller. Otherwise, you have more probability to find the particle far from the origin, which would be weird. And so it's sort of built in. These functions know that they have to get small at large distances. All right, some other properties are, first of all, they satisfy orthogonality. So I'm not going to prove this. I'm just quoting this from the mathematical study of spherical Bessel functions. If you do an integral from 0 to infinity of a spherical Bessel function, and I'm going to rewrite this in terms of k times r instead of rho. And I'm multiplying together two spherical Bessel functions with different values of k. So one of them is called k and the other one's called k prime. And then because we're in spherical coordinates, I'm multiplying by r squared dr. This turns out to be equal to pi over 2k squared times a delta function, k minus k prime. So that says you get 0 unless k equals k prime, and then you get this quantity on the right side. Okay, so now we're going to try to put everything together here as far as our wave functions. So remember, we started off on a quest to find the wave functions for E, L, and M as a function of three-dimensional coordinates. And what we found is, well, I'm going to write here a unknown constant, which I'm going to call A. And then I'm going to multiply by the spherical Bessel function. And then I'm going to multiply by the YLMs that we factored out. Okay, so this is our inner product with ELM, the ket. Okay, so the interpretation of these things is these are stationary state, meaning they have well-defined energy, spherical waves for free particles, to be contrasted with the plane wave solutions for free particles that we mentioned earlier. Okay, and so if we've got these things, they satisfy the following equation. Let's say you do a three-dimensional integral over all space. So by the way, the reason we're using the j's here and not the Neumann functions is because I'm now integrating over all space, including the origin. So I don't want to include the Neumann function solutions in this particular situation. Okay, these satisfy that if I take the complex conjugate for E prime, L prime, and M prime, and I multiply by the stationary state for ELM. Okay, now I'm basically just going to be putting together the integration for R, which is here, and then the integration for the spherical harmonics. Okay, and so this is equal to, first of all, the normalization constant I'm going to pull out front, and it gets squared. And then there's pi over 2k squared delta k minus k prime. And then the spherical harmonic part just says L has to equal L prime and M has to equal M prime. Okay, and this is because this is the inner product. Okay, so that's an orthonormality condition, provided that we choose our constant here appropriately. And so we see that to make this be nice, what we're going to do is we're going to choose it to make this expression equal to 1. So we can choose our constant, our normalization constant, to be square root of 2k squared over pi. I guess I could have pulled out the k squared and made it just a k, multiplying the whole thing. But if we do that, then the following things are true. So first of all, rewriting the orthonormality condition, it just says this. So E prime, L prime, M prime as a function of R star psi E L M as a function of R. That equals delta of K minus K prime, delta L L prime, and delta M M prime. So this is orthonormality in terms of KLMs. So by the way, we made a choice here that wasn't completely inevitable. We chose the orthonormality so that there would be a delta function of K minus K prime here. But it turns out, and some books do it a little differently, you could have chosen this so instead of K minus K prime, it was E minus E prime, and that would have been a different normalization. So that was a choice that not all books are the same on. But in any case, the last thing we can do today is we can look at this inner product of R prime with R. So that's equal to, using completeness, an integral over K, a sum over L, a sum over M, the allowed values of M, and I'm putting in here a complete set of states. Okay, so on the one hand, the left-hand side is a three-dimensional delta function, because that just comes from the definition of the Ketz of position eigenstates. Okay, and on the other hand, the right-hand side is equal to, just rewriting the integral, but now in terms of wave functions. Okay, so there's a complex conjugate and then a psi ELM. Okay, so this was the orthonormality condition for these plane waves, or not plane waves, spherical waves. And this is the completeness condition. This is completeness in K and L and M. All right. So among the things we can do with this are not just study plane waves, or sorry, not just study free particles, but study things that are free particles in certain regions. So next time we'll be studying what happens when you apply this to, for example, a particle in a spherical well, where the well, inside the well, it behaves like a free particle, and out it behaves like a free particle with a different energy. So we'll get to that. We'll also discuss the relationship. So next time, the relation of these plane waves to, of these spherical waves to plane waves. Okay, so there's a nice equivalence you can write where you can write a plane wave in terms of spherical Bessel functions, or the spherical Bessel functions in terms of plane waves. So we will do that next time. All right, so you should have all gotten your midterms back. I think we did pretty well on them. I think there was a little bit more problems, a little bit more difficulties on problem 2. So my current leaning is that your next homework set, which will come out on Friday, you'll get to redo at least problem 2 on the midterm on there. I noticed most of you turned in your midterm, so I will have to post the midterm or email them to you. I'd prefer to put it on the web page, but I may not be able to do that because NIU's VPN network seems to be down. They seem to have forgotten to renew their VPN certificate, which is not ideal. But so yeah, so there will be 3 more homework sets this semester, and they will be due a week from Friday, and then the next Friday, and then the last one will be due on the last day of class. Okay. All right, are there any questions on today's lecture or anything else having to do with the course? No? All right, so